This video is an example of the Chi-Square goodness of fit. Suppose a consumer affairs representative for Mars Incorporated claims that M&M's plain chocolate candies are mixed such that each large production batch has the following percentages of colored candies: 10% brown, 20% yellow, 30% red, 10% orange, 20% green, and 10% blue. So basically we want to test whether or not that the M&Ms actually follow this claimed distribution. So we want to determine whether there is sufficient evidence to conclude that the percentages are different from what the representatives claim. So to state the null and the alternative, one way to do it is to state the null and the alternative, or at least the null, in terms of the given proportions or claimed proportions. Now, the manufacturer is not claiming that the colors are distributed the same. In other words, they're not distributed in a uniform manner. We could easily do a chi-square goodness of fit to test whether or not this is a uniform distribution. But we're given the claim parameters, proportions in the problem. So 10% brown, 20% yellow, 30% red, and so on. So in terms of proportions, I'm just going to put in exactly what is claimed by the manufacturer as decimals. I didn't really give myself a whole lot of room here. Okay, so this is the null, and this happens to be the manufacturer's or the representative's claim. So the null is the claim in this particular example. So for the chi-square goodness of fit test, the general structure of the null and the alternative is that the null is the values are following some sort of expected distribution, either uniform or not, versus there is at least one proportion that is different. Okay, so it just takes one of these to be off just enough to drive rejecting the null. Okay, so the alternative would be that there is at least one difference. Okay, so we're given the observed values in a table. For this particular example, the sample size was 929. Okay, so there were 929 altogether M&Ms that were sampled. Okay, so our sample size is 929. Okay, if I summed up all of these values, I would get 929. Okay, so according to the problem, the professor distributed bags of M&Ms and the students counted the numbers of candies in each color, and I'm assuming they were eaten. That's what I would do. Okay, so these are the observed values. To get the chi-square test statistic, we're going to need the expected values. Okay, so the expected value calculation needs these percentages, and it needs the sample size. Okay, so I'm going to go ahead and I guess I can do it here. These are the observed, and then we need the expected, okay, for each category, for each color. So to do that, I need to multiply each proportion or each percentage by the sample size. Now, this isn't that difficult, but I'm going to have my calculator do this for me. What I did before I started recording was in my stat menu under edit, I put the observed counts in list 1 and the expected percentages in list 2. to get the chi-square test statistic either by hand or directly from this calculator, I'm going to need another column of the expected counts, not just the percentages. If you're using technology, like a computer software program, a statistical software program, some packages will calculate the chi-square test statistic with just the expected percentages, but the calculator needs the expected counts. So I can quickly do that by up arrowing to list 3, and then if I press enter, I get my cursor down at the bottom, and I just literally want to take 929 and multiply it by all of those percentages in list 2. So it will populate my list 3 with the expected values. Okay, so if you were doing this by hand, these are the numbers you would need. Okay, and also to get this from the calculator, which I will end up doing, I will need this column. Okay, so the expected counts for the first category is 92.9. I have 185.8, 278.7. I'm writing a little too large for these boxes. Okay, so the observed value for brown is 99. The expected, if we were to do this experiment over and over again, we would expect about 92.9. Now I know we can't, well I guess you could have a fraction of an M&M, but typically they're whole M&Ms. Okay, but we're going to go ahead and leave it like this, just in case you need to input some expected values into your homework and they want you to carry it out 1 or 2 decimal places. Okay, so I have the pieces I need to calculate the test statistic. The test statistic in this case is the sum of the observed values for each category, or in this case each color, minus the expected values. I'm going to square that and then divide by the expected. Now this is for each category. Okay, and then I'm going to sum all of those up. So if I were to do this by hand, I would take the observed for brown, so that would be 99, minus the expected 92.9, square that difference and divide by the expected, and then add it, to the next category, which is yellow. The observed was 221 yellow M&Ms minus the expected. We expected 85.8. We square that difference and then divide by the expected for that category, and so on. So you want to do that for each color, observe minus the expected squared, divide by the expected, and then add them all up at the end. So it's not that this is difficult, it's just a little lengthy. And if you round too much in between steps, your final answer may be a little too far off for you to get it correct in your learning management system. So I'm going to go ahead and use the calculator built-in goodness of fit function to get the test statistic directly. So I want to go back to stat, see if I can get that a little more clear. Sorry, this looks like this is as good as it gets. So I'm going to press my stat menu, arrow over to tests, and either scroll up or scroll down to find the Chi-Square GOF. That stands for goodness of fit. This Chi-Square test right above it is the Chi-Square test of association, or the Chi-Square test of independence, which is a different test. Okay, it's the test we use to test whether or not we have a relationship between two categorical variables. The goodness of fit is used to assess whether or not an observed distribution fits an expected distribution. All right, so I'm going to select, I'm not done with this yet. I'm going to select chi-square goodness of fit. Now you have to remember where your expected and your observed values are. Again, you can't use the column of percentages, you have to use the column of counts. So I had the observed counts in list 1. The expected are in list 3. And the degrees of freedom, this DF here, is the number of categories minus 1. So I've got 1, 2, 3, 4, 5, 6. So I have 6 categories, so that makes the degrees of freedom 5. And I'm going to calculate. So the calculator will do this summation for you. And that turns out to be 10.354. Okay, so altogether, if I did this for all categories and if I didn't round too much, I would get a test statistic of 10.354. Now, if I were going to compare this to a critical value using the chi-square table, I would find an upper tail area to the right that contains 0.05 amount of area with a degrees of freedom equal to 5. Okay, so depending on your table, some tables might read from 0 up to chi-square. Some tables read from the chi-square value to positive infinity. The chi-square test goodness of fit is typically a right-tailed test. Okay, if overall our observed values are close to what we expect, this difference in the numerator and all of these differences, if they're pretty close together, would be pretty close to 0. Okay, so our test statistic would be small if what we observe is close to what we expect. So that would give us a situation where we would fail to reject the null. The further we go out in this tail means that one or more of these categories are, the observed values are way off from what we expect. So the further we are away from 0, the more likely we are to reject the null. Now, going back to my calculator, I'm not going to find the critical value for this problem, but you just have to keep in mind that you would want an upper tail area of 0.05 and your degrees of freedom is 5. I'm going to use the p-value method. Okay, so what is really nice about the calculator is that it will spit out the p-value for you. Most chi-square tables are limited, just like the t-table, so to use the table to find the p-value, the best you would get would be an interval that contains the p-value, so it's not as accurate. So this p-value is 0.066. Okay, so let me make some more room here. My p-value, remember that's the probability you get a test statistic at least as extreme as the one obtained by the sample. So it's the probability associated with the test statistic in terms of being more extreme. Okay, so the p-value, I just forgot what it is 0.066. Now, to use the p-value method, I'm going to compare it to the level of significance, and that was given to be 0.05 in this case. All right, so I have my p-value, and I'm comparing it to alpha. Okay, my alpha was 0.05. Okay, this is greater than 0.05, so the decision will be to fail to reject. Okay, we're going to fail to reject the null. Okay, so visually what that would mean is that our test statistic, and it's pretty close here, would be somewhere right here. Okay, if our level of significance was changed to 0.10, this p-value is less than or equal to this, and the decision would be to reject the null. So it's important, if you're using the p-value method alone, to keep in mind what is the level of significance. Okay, if it's greater than your level of significance, you're going to fail to reject. If it's less than or equal to, you're going to reject. Because the p-value is the area associated with the test statistics. So clearly this area from my test statistic to positive infinity is greater than this little rejection area. Okay, but if my level of significance was 0.1, then my test statistic would be inside my tail of rejection. Okay, so the decision is to fail to reject the null. Okay, I'm going to base my decision off the nominal level of significance. So I'm failing to reject the null. Okay, so I am ruling in favor of the null based on the evidence. And looking at the question, determine whether there is sufficient evidence to conclude that the percentages are different. Okay, well that is the alternative. If we had rejected the null, we would be in favor of saying the proportions are different. So there is insufficient evidence to conclude that the percentages are different. In other words, there's insufficient evidence to reject the claim in this situation. Because we are failing to reject the null, it is possible a type 2 error may have been committed.